Hello, welcome to this report and presentation on dynamical systems to fluid dynamics, Navier-Stokes, exact coherent states, turbulence, ladders, and snakes. So the thing we were doing here today is exploring a few ways in which dynamical systems has been applied to fluid dynamics and progress made therein. So of course, Navier-Stokes is the generalized fluid flow equations, the most brutal things known to man because of how general they are, and they're not even proven to be perfectly well defined for all possible starting conditions in 3 dimensions, I believe, for all time. But that's a story for another time because they work remarkably well. They're incredible. They're great. But they're way too difficult to use in general for most things. So lots of techniques that have been applied to fluids necessarily have been basically truncated in their complexity with a lot of heuristics and nonsense and other things to make it simple, just due to how bloody complicated Navier-Stokes is. Because contained within Navier-Stokes, or at least fluid stuff in general, right, is turbulence. And turbulence is one of the most intractable unknown phenomena so far still, due to its infinite cascading complexity. But even with that, it turns out we've made a lot of progress in general over the last 20 to 30-ish years in this domain of fluid dynamics. So let's get started. So here we have something called Couette flow, and Couette flow is just a very, very simple type of fluid dynamics, I guess, that is very well known because of its simplicity, because of its experimental simplicity and its analytical simplicity. That doesn't mean it can't not be complicated, though, because you can, and in fact, a lot of our stuff that we're going to talk about comes from more complex analysis of Couette flow. But it is still like, it's not like we're just pouring water into a cup, right? How do you even begin to model that? This is Couette flow, where we have two planes that are sandwiching a fluid in between them, and the planes move relative to each other, and that causes a shear stress, and that causes fluid flow to occur within the sandwich. And this is the plane version on the left, as you can see, and this is the cylindrical version on the right. So the cylindrical version is great because of its experimental simplicity. It's a lot easier to get cylinders that are very long and fill them with fluid and then do analysis on them than it is to have very flat, wide sheets and then that are trying to sandwich fluid and then move them and then try to do analysis on them. So cylinders are used a lot in a lot of experiments. And one of the other interesting things about cylinders is that they're cylindrically symmetric. So they have let's see, they're finite in two directions. They're finite azimuthally and finite in the s-hat direction. Whereas the plane version of the Couette is well, actually, I guess this thing it's finite this way. Actually, yeah, wait, it's only finite in one direction. All the other in the other directions, it's infinite. So that cuts down a lot of the complexity of the a fluid analysis in a lot of ways, because of the fact that due to the symmetry and the fact that it's binded like this. And one fellow named M. Nagata performed some analysis on this geometry, and he was able to make some interesting, he was actually able to come up with some solutions that led to turbulence, which was very, very good, because at the time in 1989 there hadn't been anything like that, I don't think. So the thing that he did was he well, he did analysis on that structure, the cylindrical structure with the water in between the two cylinders, and he made some more, good approximations. Like he made it so that the distance between the two cylinders was very small, so that locally it was very very similar to like a plane couette structure, plane couette flow, and that also gave him some good limiting approximations that he was able to use, because at the time, linear analysis, what do they call it? Linear analysis of the flow in this geometry, in this regime, showed no turbulent sort of sticking points, or no turbulent like manifestations, basically, from infinitesimal perturbations in the flow, regardless of the Reynolds number. And the Reynolds number is something that's very important in any fluid dynamic thing. Basically, the higher the Reynolds number it is, the more easy it is to be turbulent. So even if at arbitrarily high Reynolds number, there didn't seem to have any manifestation of it, and that was weird because, of course, in experiments, noted turbulent behavior. Experimentalists in the real world noted turbulent behavior with a high enough Reynolds number, and of course with other there's that was a narrow condition, but there's a way to get turbulent behavior from it spinning fast enough, but that's not really what we're talking about here. So what Nagata was able to do was somehow analyze this and come up with something very fancy called bifurcation from infinity, where somehow he escaped the issue of like having arbitrarily high Reynolds numbers not lead to any turbulent stuff, where somehow, and this is something that's complicated and weird in a mathy way, there's like a limiting, as if something is coming from infinity, so it's not like it's arbitrarily high, it's as if it's kind of like there or something at infinity. But he did something like that, and he was able to come up with stuff that led to some turbulent stuff, like so he actually got solutions, some real good solutions, and that was incredible because, yeah, I mean, this is like, I think, one of the first times that they had solutions of that caliber, of course, in this way. So that was incredible, but one of the issues with that is that the domain in which he was working in was very small, necessarily, right? In order to develop the theory, he needed to start as simple as possible while still getting interesting behavior. So due to the geometry and the nature of the analysis that he did, the solution that he's discovered, or solutions that he discovered, would be known as periodic, which means that they're like kind of bounded, or they're periodic in like time or space, and that makes them a lot easier to analyze, of course, just due to the fact that it's the same everywhere, across a certain length or scale, but that also meant that there was a lot of very interesting, complicated behavior that was not quite captured, and that type of behavior would be called like localized, turbulent stuff in a scientific way, and that localized incidences of turbulence, oftentimes called slugs, couldn't be captured by the periodic behavior because it was too simple. It was too, in some sense, homogeneous. So it wouldn't be able to capture like a random turbulent puff appearing out of nowhere, and then what happens with that. So one of the next things that needed to happen was being able to figure out how to sort of take steps in that direction, like how to sort of figure out how to where localized solutions could come from. Localized, like as in, where could some turbulent thing arise in a singular area in some large space. So this is what Schneider and et al. Did in 2010. Um, they made significant progress using a lot of complicated mathematics in plain Couette flow. Let's see. Yeah, so they did a lot of complicated stuff. Very, very cool though. They were able to like basically show that there was a large number of exact localized solutions that existed. And the interesting thing is that they, it also demonstrated this snakes and ladders. That's what they call it, the snakes and ladders shape in the in this plot. So this type of behavior is really interesting. It's also okay. So its more formal name is called like homoclinic snaking, but it's basically where like a sort of trajectory of a system behavior oscillates between something that is more periodic and something that is more uniform, or something else basically. And this is also related to something called the Swift-Hornberg equation, which is very good because the Swift-Hornberg equation is like a pattern forming equation, and it's basically, it has very similar vibes to like this. And because it's so well understood, if there could be like more definitive connections made between this domain and like the behavior of the Swift-Hornberg equation, that would be a massive insight into like fluids in general, of course, especially with turbulence. So the snakes and ladders, homoclinic snaking, the reason it's called this is because it snakes down over here, blah blah blah, and also there's a ladder. Those rungs are, I think, transitions between different states, I think. And these are two different solutions. Here's the traveling wave solution and the equilibrium solution. And so this is, it's really, so the reason why this is so interesting, and the reason why this was connected to the periodic solutions that we discovered before, is that like the periodic solutions are even more useful than was anticipated, in the sense that like it turns out a lot of like real localized solutions look very, very similar to the periodic solutions a lot of the time, and that's what this is doing. It's circling, or it's going back and forth between looking like a periodic solution and then going back to some uniform thing. And within there is like turbulent behavior in that process, and that is really, really interesting, because that means there is like there's like we have a grasp now. We have something more so, and the periodic solutions basically kind of stand up, or they're exact. They stand in this massive possibility space as pillars of like of exactness, but of sort of like something that other solutions, more complicated solutions, can kind of emulate in sometimes at least. So, which is great, because that means that like they might be sort of like a generic structure form of solutions in general, and it seems potentially that more complex solutions could be something like jumping from one periodic solution to another, and just doing that, and that could be a turbulent thing in and of itself. Where in this homoclinic snaking, you basically, there's this oscillatoriness that means that like you in some abstract space, as you get closer to some, there's this point that has periodic behavior, and you get close to that, the more the solution, or the more the configuration, whatever is going on, is looks like a periodic solution, and then it'll circle back, and then it'll be more like of a uniform solution, and that's neat. Because, like I said, because of the fact that we understand, since we understand the periodic solution so well, that means we can make a lot of like progress on these localized things, which is great. And the fact is, the biggest thing is that the fact that there's a demonstration of the existence of these localized solutions with this sort of behavior. It means that there is other solutions that also have this similar sort of snaking behavior, close to, that look similar to some periodic solution in other context, which is great. That's a huge progress. That's huge. So yeah, that's one of the biggest ways in which this thing was going on, and this is like, bifurcation, blah blah blah. There's a lot of this is a very very thick topic, which makes sense. It's fluid dynamics. There's lots of papers making tiny little progress, but each one is like so deep and so dense. It's crazy, and it's actually really cool. And of course, they have plenty of lovely diagrams like this. Yeah. So let's see. Yeah. So periodicity in the Swift-Hornberg equation. Swift-Hornberg equation, like I mentioned before, is very well known, and if there is and it has stuff that, let's see. And it has homoclinic snaking, and that's why there's more relation to the snaking that we've observed here, and that's really good. Yeah. So if we're able to make even deeper connections with the Swift-Hornberg equation and these localized solutions, or solutions in general, to fluid dynamics, to certain fluid configurations, and maybe even more so, we would gain a lot of incredible insight into how it might function even more so, just due to the fact that how well understood this thing is. And this is a pattern forming differential equation, and that's really cool because we could see patterns in turbulence, which would be crazy considering how crazy turbulence is. Yeah. And here's the references. Boom. Any questions?